Welcome back, everyone. We're going to talk about the basic functions. I mentioned a little bit about that in the last video or the last lecture. These are some of the basic functions. Now, why do you want to know about those? Well, it's sort of like this. These are sort of a starting point for seeing what a graph of something looks like. The identity, for example, squaring, cubing, really basic. And these are sort of the inverses of those. Absolute value means sort of you throw away any minus sign because it also represents how far a number is from the origin. Piecewise defined functions, a little bit strange, but there are lots of applications that use piecewise defined functions. We'll have one example in here, and I'll leave it to your imagination and your exercises to really get that solid. Okay, continuity. Sounds complicated? It really isn't. It just means that you got a graph. If you can draw the graph without lifting your pen, then it's continuous. If you have to draw it like this, those different sections, it's not continuous. Because as soon as you get here, you have to lift the pen, come down here, and start over again. That's all it is. So, with that in mind, could you describe the intervals of continuity for each function? In other words, where is it continuous? Here's y equals x squared, for example. Where is it continuous? Well, remember, this arrow means that it continues forever in the left-hand side and in the right-hand side. So imagine you were able to draw and you came here. Well, you wouldn't have to lift your pen beyond that. If you had enough time, an infinite amount of time, you could draw the whole thing in without ever lifting your pen. How about this one? Well, this at first glance might look like it's continuous, because if you start from the left, you can draw, everything goes well until you hit 3. You're not allowed to use that 3. So you have to jump your pen over to the other side and start over again. It's continuous here, it's continuous here, but not the whole place. Excuse me. So the domain, for example, consists of everything up to 3, but not including it, and everything after 3. Okay, now we're going to get to the basic functions. Now the idea is like this. The identity function, I'll give you an introduction here. Looks something like that. It's at 45 degrees in case you're interested. Now, the reason we're doing this is if you can start with the identity function and make a few changes, maybe you could take this whole thing, and let me change the pen color here, change it to blue temporarily. If I took this line and just grabbed a hold of it and moved it down, it might look like that. The key is, if you know what this one looks like, and you know how these various changes affect the graph, you can go from this to this in no time at all. But you need to know what the basics are. So that's the idea. I'm going to change back to red so you can see it a little bit better. So there's the identity function. Remember, it's the same thing as y equals x. In other words, the x and the y values are exactly the same on this line. You can tell it's a line because x is the first power and nothing else. Excuse me. And that's what it looks like. Now, if you look closely, you'll notice this doesn't look like it's 45 degrees. That's because this is twisted out of shape. Sometimes graphing calculators, this is from a graphing calculator, sometimes they don't get everything in the right perspective. But you get the idea. For example, somewhere in here is the point 5, 5. For each one of those points on there, the x and the y coordinates are the same. That's the identity function. So you start with a number, and the number that's paired up with doesn't change from the original number. Domain and range, all real numbers. Because if you think of from left to right, there's no number you can't use for x. And by the same token, on the vertical axis, that line at some point it's any value at all if you go up high enough or low enough. So here's what it looks like. Domain and range are all real numbers. You know, sometimes I describe it like this with this fancy R. Domain and range, notice it's increasing everywhere for this one. As you go from left to right, it's going up. And it's continuous because you can draw this without lifting your pen. The second of these basic functions is the square function, and it looks like this. And for the last time, y equals x squared. And you can graph that on your calculator. Good practice if you haven't done it before. And that's what it looks like. Now this is, just like the other ones, a little bit out of whack, but this actually shows it pretty well. That's basically what it looks like. Also, you might want to know, this describes what's called a parabola. Domain, what x's can use? Anything. Anything can be put in x. You can square any number, but what do you get? When you square it, you never end up with a negative. So the range starts at 0, goes to positive infinity. If you're actually graphing this, my suggestion would be, first of all, if you notice this isn't a linear function. So you're going to need a number of points, probably 5, 6, 7 points, until you can see where the non-line goes or where the curve goes. Now what I do when I need several points is I'll choose a negative number, I'll use 0 for x, I'll use a positive number, and in this case where we need some extra ones, I'll just throw anything else in at all. But the point I'm making is use some negatives, use 0 if possible, use some positives. And by the time you've graphed those, you should get an idea of what's going on. So it decreases. Remember, the decrease means what's the y value? It's getting smaller and smaller until it hits x equals 0, y equals 0. After that, it starts increasing. And that's what it's talking about. Decreases to the left, on the left, and increases on the right. Remember, we're always talking about left to right. And it's also continuous because you can draw this graph without lifting your pen. Well, if we've got a squaring function, how about a cubing function? Same thing. Remember, that's the same thing as y equals an x cubed. And this is what it looks like. Now remember, the squaring one looked like this, so don't get them mixed up. I don't think you will. This is the squaring one. This is the cubing one. It resembles a little bit the squaring function on the right. It actually isn't the same. The squaring function would look more like that. So this is squeezed closer to the y-axis, or another way of saying it is that as it goes from left to right, this gets higher and higher and higher, but faster than this does over here. And on the left, it goes in the opposite direction from what this does for the squaring function. So this is the cube function, or cubing function, and this is what it looks like. Domain and range, if you look at the x's, any x can be used at all because you can put any x in this x, cube it, and what you get out is, if you're cubing it, you can not only end up with a 0, you can end up with positive numbers, you can also end up with negative numbers. For example, put a -2 in there, cube it, -2 times -2 times -2, you get -8. So you can get any real number in the range. Again, if you want to actually graph this on your own paper, remember I said use negative numbers, use 0 if possible, throw in some positive ones, because your function, whatever it is, might do things a little bit differently for 0, for negatives, for positives, and you want to see what's going on. Again, domain is all real numbers, and it's continuous everywhere. You don't have to lift your pen to draw this. Now, if we've got the squaring function, how about the square root function? Well, very simple. By the way, I'll give you a tip. Excuse me. There's another way of writing this. Now, we'll get back to this later, but you can also write it as x to the 1/2 power. Now, don't let anyone know I told you this, but this is something that's coming up at some other point. That's just for your information. Don't let anyone know it, though. And this is what it looks like. Remember, the squaring one looked like this, and this one looks like we took half of it and erased it, and then switched it around a little bit. Well, that's true, and the reason there aren't any numbers down here is that this is a positive square root. So you only get non-negative answers, only 0 or positive answers. And you can't put negative numbers in for x. That's why there's nothing back here. So as the domain, we had to stick to the non-negative ones, or 0 plus the positive, and the range, same thing. You can't end up with a negative because it's the positive square root. And if you're graphing it, remember, you can only use non-negative x's. So since you can use 0, do it, because it's easy. And if you're clever, you're going to use perfect squares for your x's. Like 1, 4, 9, 16, 25. You probably won't want to get too big because you won't be able to graph it. And then that gives you nice, even answers for y. So increases, even though it's slowing down, it still increases forever. And starting at 0, or the origin, you can draw this without lifting your pen, because you're starting here and you don't have to lift your pen. Cube root function. Now this is very much like the cubing one. Remember the cubing one? Just for your information, looks like this. So this is rather similar. Only, as it turns out, the x's and the y's are reversed. So if you took this one over here and took your identity function and flipped it on that line, you'd end up with this. That might be a bit much to take in. The important thing is the x's and the y's are reversed. Domain and range, just like with the cubing function, all the real numbers. Again, be clever. Use perfect cubes for x's. 8, 1, 0. You could use 27, but that's a bit on the big side. You could also use negative 27, but then you'd need some big graph paper. Increasing here, increasing there, everywhere. Absolute value function. Excuse me. Okay. These are vertical lines to the left and right of the x. And what this means is, imagine here's the number line, and this is you. And you're going in this direction. Now what this absolute value function is how far are you from the origin? Well, distance is never negative. So the absolute value function is not ever negative either. You could be standing right here. So that'd be 0 for the y value. Over here, you could be 3 units away, and it'd be 3. If you were over here at -5, you wouldn't be -5 units away. You'd be 5 units away from this origin. So that's a way of thinking of the absolute value function. There's a picture of it, and it's a tiny bit misleading because this angle right here should be a perfect 45 degrees. Again, you can use any x's, or the domain is all real numbers, and the range, notice the only y's you get are 0 and positive ones, because there are no negative distances. Graph it again. There's some negatives. Our good friend 0, because you can put 0 in here. And some positives. Graph those. But what really helps is if you know these basic functions and you see this, you can draw it real fast. Even if you see something like this. If you saw the square root of x plus 7, if you know what this looks like, you can make a subtle adjustment and find out what this looks like. There's you looking at the new one. Again, it decreases here, increases there. It's continuous everywhere because you can draw it without lifting your pen. Piecewise. Okay, this is tricky. The idea is this. This tells you what x's you're allowed to use to graph minus 2x plus 5. So on your graph paper, 2 is sort of the separation point. So over here somewhere is 2. So if you're less than or equal to 2, so in this area back here, you're going to find y values using that function. When you get to this side over here, you're going to use this function to take your x's to give you the y's. We'll see that in a minute. You get a second one, and this one, 0 is your separator. Everything back here uses that to connect the x's and the y's. On this side, you'll use this function to take from an x to the y value. So let's take that first one. Remember, 2 is sort of a boundary. Everything up to and including 2, you're going to pair up the x and y's using this. So this part right here, now notice these are the numbers up to and including 2. How do you get the y values to get that point? For example, let's suppose you picked a -1 for x. That's one of these. Since it's one of these, you use minus 2x plus 5. So minus 2, there's our -1 that we're using this time. Put those together, you have 2 plus 5, or 7. If you've got a -5, -5 is still in this region, so use this. Put a -5 in there, you'll get 10 plus 5, and your point is 15. Graph several of those, but remember, don't go over that imaginary line. Now, as soon as you finish that, and you are allowed to use 2, so that's one of those points. Once you get on the right side of 2, you're talking about x is greater than 2. So if you have the number 4, for example, 4 is one of those. So you put the 4 in for this x, and so 4 will be paired with a 5. 4 plus 1. And you can take 7. 7 plus 1 is 8. Starting here, but not using the 2. So get close, see what the pattern is, and draw that line ray, it's called. Now, this is a more exotic one, but if you get accustomed to doing it with lines, this isn't a big deal. Now, the boundary is the 0. So on this side of the graph, when you pick an x back here, this is how you're going to pick the y that goes along with it. So let's suppose we take x equals -2. Now -2 is one of these numbers. So you put the -2 in for x. That'll give you -4 plus 3. So this gives you a y value of -1. So one of those points back there would be -2, -1. And that's how you work it. Graph a bunch of these, 3 or 4. Now you can see this is a linear function in this section. So this is going to be a line, so all you'll need will be 2 or 3 points to the left to that 0. And then you can draw this line in. When you've got that in, then consider x's that are bigger than 0. So for example, you could take the number 2. 2 happens to be one of these numbers. So you put the 2 in here, which gives you -4 plus 6. And you end up with 2. So 2, 2 is one of those points. 2. Have I got that right? 2, 4, 2. This might be a little bit off. Because if you put -2 in, +2 in there, you get the opposite of 4, which is -4, plus 6 is 2. So this graph is not perfect. It gives you an idea of what it looks like, but it's not perfect. Next, the greatest integer function. So for example, let's suppose, go back to the television example. How many TVs can you have? Well, you could have 0, you could have 1, 2, 3. You can't have some fraction. So this takes that number and gives you back the biggest integer to the left or at x. Now what do I mean by that? Let's draw a number line here. Let's put a 0 in here and throw in some points. Okay, up here. Let's suppose this is a 3, and we're looking at this point right here, about 2 2/3 maybe. What you want to think of to get this greatest integer function is, if you were traveling from left to right, what would be the last integer you saw before you got to the 3? Or before you got to the 2 2/3? Well, the last one you would see would be this one right here, -2. So the greatest integer for 2 2/3, remember you're traveling from left to right, what's the last integer you saw? Well, you never got to 3. The last integer you saw was a 2. So that's equal to 2. Let's go up here to 4.5. So what's the greatest integer for 4.5? Okay, start traveling from left to right. Here's 4.5. What's the last integer you saw? Well, you never got to 5, but you did pass 4. So the greatest integer is 4. Okay, that's pretty simple. In fact, most of us usually look at that, and if this number in here is positive, we just chop off the fraction part or the decimal part. It's real simple. Where it gets tricky is back in here. So let's suppose this is, see, -1, -2, -3. Let's take this point, let's say -3.5. Now we can't just chop off the 0.5 because the greatest integer says the greatest integer less than or equal to that. In other words, if you're traveling along here, what is the last integer you saw before you got to this point right here? We never got to -3. You certainly never saw -2 or -1 or 0. The last one you saw was a -4. So the greatest integer for -3.5 would be -4. If you have an exact one like this, say a -7, well, that's real simple. If it's already an integer, it's itself, period. That's easy, whether it's positive or negative. The tricky part is if it's in between them. In that case, take a look at this number in here, and if it's not equal, which is easy, look to the left. What's the next integer to the left? So that gives you two ideas about how to find the greatest integer. This is an idea of what the greatest integer function looks like. So you might look back here and see, how does this work? So if you looked at 3, well, that's an integer already, so the function value is -3, same thing. If you're talking about up here at -2.5, well, you haven't gotten the -2 yet, so it's still a -3. You don't switch over until you get to the 2, and then all of a sudden it jumps up here because the greatest integer in -2 is itself, -2. It's a little bit different. One of the reasons for knowing these basic functions is if you do have greatest integer, for example, if you know what it looks like to begin with, then you can play with maybe 1 or 2 of these steps, and then once you've got a couple of those in, you can follow the pattern for the rest. Notice a couple of things. It's constant and continuous inside some of these intervals. From there to there, it's continuous. But as a whole, the whole thing, it's definitely not continuous because you have to keep lifting your pen to get to the next section. All integers for the domain, the range only has integers. So the domain, oops, did I say range? So the domain, you can put anything in for x, but the range, it only has, oops, yeah, only has the integers. So dot, 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 -3 is a possible answer, -2, -1, 0, 1, 2, 3, and so on, all the integers. But for x's, any number will do. So, how does this work? Well, this is one of those examples where you know that it's going to be a step function because it's a greatest integer function. If this were just x in here, you know what it would look like that. But this isn't quite the same, so you might have to play around with it a little bit. Now notice that it's 1/2 x, so to make it easy on yourself, for one thing, you might want to use 0. You might want to use, since you're going to have to take the half of some number, you might make this -2, -4. That helps, because when you're taking half of it, it comes out even. You might also go with 2, 4, maybe even 6. Now, what do you get? -4 gives you a -2 here, plus 1 is a -1. If you put a -2 in there, you've got a -1 plus 1, that's 0. Put a 0 in, you get 1. Put a 2 in, you get 2. You start seeing a pattern here. The question is, what does it look between those? So what you really need to do is maybe make a second one and see what's going on with some of those other numbers in between. So we know we've got 0, 1. That's a given. That was easy. So you might want to check and see what's happening at negative 0.5 or negative 1/2. What happens? Well, if I take this, negative 0.5 plus 1, and I'm going to take the greatest integer. Now, what do I get? Well, we have to figure out what's inside first. 1/2 times 1/2 is 1/4, and it's negative, so it's negative 0.25 plus the 1, and we want to find the greatest integer of that. So what's this equal to? It's equal to 0.75. So what's the greatest integer of 0.75? Look at it on the number line. What's the last integer before you get to 0.75? There's 0, there's 1, 2's up here somewhere, negative 1, so on. Here's 0.75. What? It's not an integer, so you can't just use 0.75. So you have to look to the left. What's the next integer to the left? It's a 0. So negative 0.5, if you want to put it in here, you get 0. Get a bunch of those until you get a feel for what it looks like. I'm going to get rid of some of those marks so you can see this a little bit easier. Erase the ink. Okay. So here's some ideas. Use x's. 0 is an easy one. And you want some in between. So 0, 1, excuse me again, 2, 3, 4. Those should be pretty easy to work with. And find out what y's are generated by this function. Once you get this worked out, that might give you an idea of how all the rest work. Figure out one of them. You know, at some point there's going to be a jump, and you're going to go up here, and like this. The thing is, where is this? Where is this? Where's the next one? You need a bunch of points to tell you where to draw that basic one that you're going to use for your step. So those are some suggestions for ordered pairs. And notice the range. Since it's the greatest integer function, the range is going to be integers. Now here's a good example. It says the express mail company charges $25 for a package weighing up to 2 pounds. So even if it's 0.32 pounds, it still costs $25. If it's 0.01 pounds, it still costs $25 until you get to 2 pounds. At 2 pounds, you're still paying the $25. Once you get over that, things change. So 2.1 pounds, what happens? Well, it says for each fractional pound or fraction of a pound, there's an additional charge of $3. So y equals d of x represents the cost. Graph it for 0 to 6. So this is what it looks like. For a package, you can't have a 0 weight package, so that's why this is empty. Anything up to and including 2, you're paying the $25, which is right here. Once you go over 2 pounds, it jumps up. go up. And this is a good exercise for you. See how they got those numbers. So y equals for 2 to 3. For each additional pound, it goes up that amount in dollars. So here's the base. We just went over and the $25 jumps up to 28 because that's, well, you do the math. I'll let that to you. I know you can do that. And last of all, just a reminder, this looks like it's a function perhaps, but it isn't, because for functions you should be able to write them like this with some x's in it. You can't do that for this one. If you take this one and try to solve it for y, every y comes from two different values of x. Okay, well that's it, folks. Remember, this will give you an idea. You want x's, they're squares, so you pick these numbers, get the y's that go along with it. Ooh, I think I had this backwards, sorry. Okay, so the domain, you can only have positive. You can only have positive because you're squaring something. This has to end up being positive or 0. Put those numbers in here. Once you do this, you'll see, if you get enough points, you'll see that you can have multiple y's for each x. And that's not a function. This should not happen. Okay, that's all for this, folks. Next time we're going to talk a little bit more about graphing. But for now, try to get this one down, get those basic functions, what the functions themselves are, what they look like, so that if we had a quiz where I said, how about the identity function? What's the equation look like? And what does the graph look like? And you should be able to do each one of those in, let's say, 10 seconds. We'll give you plenty of time. So if I asked you about the identity function, the square function, the square root function, and maybe the greatest integer function, you should be able to write those down and draw them in just a few seconds. Okay, see you next time, folks. Bye.